In this video, we're going to continue solving polynomials of higher degree, but by first making a list of possible rational roots that could potentially go into something. And the reason why we're doing this again, recall that when we are trying to find the zeros or the solutions for polynomials of higher degree, our method here is to plug in 0 for y, or get everything equal to 0 here. And what we're trying to do is solve this for x. Now the hard thing here is that we have so many different types of x. So our primary method is usually factoring, but with fourth degree things like this is like a 5-nomial here. We don't have a factoring method for it. So what we're going to do is we're going to divide things out. And what this list, again, this rational roots theorem or the rational roots test, what it does is it gives us a list of possible rational roots that can go into this. So what we're going to do is we're going to make our list. So we say it's the set of numbers. We say plus or minus because recall that the set of possible things that could go into this are the factors of the constant term. So we have our constant term here. The factors of this over the factors of the leading coefficient. I'll abbreviate that LC here. So we have our constant term factors go up top. So we say factors of 12. I used that in my last video, but we say it could be positive or negative factors. So that's why we put the plus or minus out front. So we have 1, 2, 3, 4, 6, and 12 to be very straightforward about it. And then we say the factors of the leading coefficient. Those are the ones we put down here. So we say 1, 2, 5, and 10. Now this is very interesting, and as a matter of fact, something I want to point out here. In the last video, we did this when the leading coefficient was 1, and you could imagine, God, if the leading coefficient was 1, you could say forget these, and it would just be like 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, 12 over 1, which is basically just the numbers in the numerator, those factors. But when you have like 2 and 5 and 10, I'm actually going to list all these out. I'm going to do it very quickly, but remember we get 1, 2, 3, 4, 6, and 12 just by taking those over 1, but then we get 1 over 2. We get 1 over 2 as a possible answer. We get 1 over 5, or I guess we'll go through the order here. We say 2 over 2. Now that's interesting because 2 over 2 is 1. We already listed that. We say 3 over 2. So 3 over 2 we didn't list. We say 4 over 2, which is this 2 right here. How about 6 over 2? Well, we listed 3. We get 12 over 2, and we've listed 6. So that introduced 2 more possible answers here. Let's put them over 5. So we get 1/5, 1 over 5. Could be 2 over 5, could be 3 over 5, could be 4 over 5, could be 6 over 5, could be 12 over, and you can see how this list, when this leading coefficient is not 1, grows immensely. So I am going to finish this list here. We say, okay, now we've got a 10th. 1 over 10 is a possible answer. 2 over 10, but that's a 5th, so we already listed that. 3 over 10, so we haven't listed 3/10 yet. 3/10 is possible. 4 over 10, which is 2/5. We've already got 2/5 on the list. And then we say 6 over 10, which is also, well, that's 3/5. We've got that here. And then 12 over 10, which would be 6/5, which we already have. So this is our list of just the possible things that could potentially divide into this evenly. So what we're going to do is, of course, we're going to start with easy ones. But you could notice here, if I guess with 1 and -1, they both don't work. Then maybe I try to divide out 2 and -2, and they don't both work, and maybe 3 and 4. Maybe I make it all the way through the whole numbers here, which actually happens on this one, and none of them work, and I got to start using these fractions. The thing I want to point out here is this. When you have a leading coefficient that is not 1, it's really beneficial to you if we just go graph it, okay? So when I say the leading coefficient is not 1, the results of the rational roots test can increase dramatically, which we've seen here. So it says in such cases, it's also beneficial to sketch a graph of the function for the, first, and then, on a graphing utility. Now, usually we have a graphing calculator, keep in mind. And on a graphing calculator, the picture is not as detailed as, this Desmos generated graph. But we can see here our x-intercepts. Now, when I hover my mouse over this, you can see the actual decimal values of the roots here. But the thing I want to point out here is this. What I'm trying to determine is, are there any numbers on this list that I should try to divide out that are also on my graph? So when I look at this, I say, well, I don't recognize, you can see a ghost 1.618 there, and 0.8. Well, that's actually 8/10, and was 8/10 on our list here. Now we didn't have 8/10 on the list, but we did have 4/5, and 4/5 is actually on the list. So I suspect that 4/5 is a 0. Negative 0.618, I have no idea. And then we say here negative 1.5. So how do I get this negative 1.5? Well, that would be our 3/2 right here, and we've got 3/2 listed right there. So you got to be keen on these things. And what we're going to do is that we're going to pick one of those that we suspect is a 0, and we're going to try to divide it out and then go from there. So we have our coefficients, not needing to fill in any zeros on this one because all of our terms are present here. we suspected out of like 4/5 and 3/2, I'd rather go with halves here. But we'll carry down the 10 and we say, well, what's 10 times 3/2? Now really, okay, so we don't have this working for positive 3/2 here, so I kind of went off on a tangent. I listed positive 3/2 and I recognized that we were saying it's negative 3/2. So let's try this again here. We say negative 3/2. What we're going to do is we're going to insert our coefficients here into our array. So we say 10, negative 3, negative 29, 5, and 12. And then we'll put in our appropriate negative 3/2 here because that's the x value we suspect. We say carrying this down again, we say 10, negative 3/2 times 10, let's see, negative 3/2 times 10. These would cross cancel. This becomes a 5, so we get negative 15 this time, which makes this a negative 18. Now, negative 18, if we take that times negative 3/2, negative 18, these would cross cancel. We get a positive here. But this would become a 1, this would become a 9, so 3 times 9 is 27, plus our negative 29 is negative 2. Negative 2 times negative 3/2, okay, so we get negative 3/2 times negative 2, which makes this a positive times a positive, but these cross cancel, becomes 1, so we get 3 here, and then plus our 5 is 8, and then we have 8 times negative 3/2, so we'd say our 8 cross our 8 cross reduces here with this 2 to give us a 4. So negative 3 times 4 is negative 12. And we can see that we do indeed get a 0 here. So we have a remainder of 0. And what this means is this is indeed one of our zeros. We say that's our 0. It also means that x plus 3/2 must have been one of the factors. And it also means this, with this remaining quotient right here. We actually have 10x cubed minus 18x squared minus 2x minus 8 here, and what we would try to do now is we would actually try to factor this by grouping, which doesn't work. So again, what would we do? And the thing I want to point out here is this, and I'm going to kind of block this off. When you get in a situation where it doesn't factor, what you have left over doesn't factor, then maybe what we need to do is recognize that we could keep going with these factors that we have right here. So again, what if I were to make a new array? And I say, well, I've got now 10x cubed minus 18x squared minus 2x minus 8. And now I'm going to try a different 0. And remember, we had suspected that 4/5 was one of our zeros, and that's a positive 4/5. So I'm going to write a positive this time. But let's try this out and see if we can get it to work. So we say carry down the 10. 10 and the 5 cross reduce, and the 10 becomes a 2. So 2 times 4 is 8, plus a negative 18 is a negative 10. The 5 and 10 cross reduce again. This becomes a negative 2 this time. So we get negative 2 times positive 4 is a negative 8. These add up to be a positive 10, and then we say 10 and the 5 cross reduce, you get 2, 2 times 4 is 8, and here's our other 0, okay? So again, I got a remainder of 0, which means now we've got another 0 here. We say 4/5 was another one of our zeros. I'll kind of block these off here. These are solutions that we are listing right here. But 4/5, we got another one to work, which means x minus 4/5, that's an ugly 4. X minus 4/5 must have been the factor. So we say, what's left? Well, we have 10x squared minus 10x plus 10. But here's the thing, this is our factored polynomial based upon the zeros that we're finding. So this is our factored original polynomial, f of x here. It's just that we've been breaking it down, and I want to point this out. This 10x squared minus 10x plus 10 we could factor a GCF out of that, a 10. So we could say, 10 out front, we say x plus 3/2, and x minus 4/5, and this would now become, just 1x squared minus x plus 1. But the thing I want to point out here is this isn't factorable. So going back to the graph again, I notice that I get 2 more zeros here, negative 0.618 and 1.618. But the thing I really want to point out here is this. This right here would have to be solved with the quadratic formula because we can't factor it. But the point here is this. We are able to find all these real zeros by breaking things down, starting with this rational roots test. And sometimes it's really good to look at the graph first. Cheers.